All right, let's look at the next example. Let's say this time second order ODE. Find the general solution. Of y double prime plus y equals 0. So again, this is the second order ODE that we have solved it before. We have found the general solution before in chapter 2. This time we want to solve it using power series method. So again, I can give you a recall that from chapter 2, the general solution, we wrote it as y equals a0 sine x plus a1 cos x. So this was the general solution. General solution of this ODE. Now we want to verify that this is the general solution for this ODE, this time using power series method. So again, the first step would be to start with some point x equals x naught, which is supposed to be an ordinary point for our ODE. So here, again, P of x is 1 because the coefficient of y double prime is 1. So P of x is 1. So that means any point is an ordinary point for this ODE. So that means we can choose any x equals x naught as an ordinary point for this ODE. Again, remember that x equals x naught would be an ordinary point if P of x naught is not 0. And here P of x is constant function 1. So P of every number is non-zero. So again, the easiest choice for x naught would be naturally x naught equals 0. So choose x naught equals 0. Then we will have y equals sigma a n x to power n from 0 to infinity. Because in general it's a n x minus x naught to power n, but here I'm choosing x naught to be 0. So my function will be sigma a n x to power n from 0 to infinity. Now I need to substitute back into this ODE. So substitute back. Substitute back into y double prime plus y equals 0. And then what do we get? First, I need to differentiate this function because y double prime is appeared there. So first I need to find y prime, then y double prime, then I can substitute back. So y prime, here y prime will be derivative of this function. And that will be sigma n a n x to power n minus 1 and from 1 to infinity. Now if I differentiate one more time, will be sigma, so derivative y double prime with derivative of y prime, which means derivative of n a n x to power n minus 1 and from 1 to infinity. Then derivative, that's going to be sigma n n minus 1 a n x to power n minus 2 and from 2 to infinity this time. You also say n from 1 to infinity, but again, if you replace n with 1 here, n minus 1 will be 0. 0 times anything is 0. So this is equivalent with saying that you're starting with index 2 here. So this is y double prime. Now if I can also write this one before substituting back. Let me change this power to n, x to power n, because for original function y, we have x to power n here. So let me also replace n with n plus 2 so that this power converts to n. So if I change n to n plus 2, Then I'll have sigma n plus 2 times n plus 1, and from 0 to infinity a n plus 2 x to power n. I've changed n to n plus 2. This becomes n plus 2. This becomes n plus 1. This becomes a n plus 2. And this becomes x to power n. And the index, starting index, shifts 2 units to the left. So it starts from 0 to infinity. Now, if I substitute back, I know that y double prime plus y equals 0. So then I'll get sigma n plus 2 times n plus 1 a n plus 2 x to power n, and from 0 to infinity, plus sigma y, which is sigma a n x to power n, and from 0 to infinity equals 0. Now again, I know that if I have sigma, let's say bn plus sigma cn, I can write it as sigma bn plus cn. So I can combine these terms and write it as, all of them are x to power n here. So these two match. These powers match. And these indices also match. So then that means I can just combine them. And write it as 1 sigma in the form n from 0 to infinity, n plus 2 times n plus 1, a n plus 2 plus a n times x to power n equals 0. So see, if these powers, for example, didn't match, I could not have, just simply added the coefficients. Or if these indices didn't match, let's say it's from 0 to infinity, this one 1 to infinity, then I couldn't have just said 0 to infinity, because then one of them 0 to infinity, one of them another. So it's important that before you combine, you make sure that these powers and these indices match together. Now that we have sigma, some coefficient times x to power n equals 0. So this 0 means identically 0 for every x. So that would happen if every coefficient in the left-hand side is 0. Then we can say that n plus 2 times n plus 1, a n plus 2 plus a n equals 0 for every n bigger than equal to 0. And this gives me my recursive relation. Remember the goal for substituting back, writing as a power series function and substituting back, the goal is to find a recursive relation for an, which means a relation that gives an in terms of the previous ones. Or let's say an plus 2 in terms of previous one, doesn't matter. And then we can use the recursive relation to find, let's say, AIs in terms of A0, or in the case of second order, AIs in terms of A0 and A1. And then we can find the general solution. So here the recursive relation would be an plus 2 equals minus an divided by n plus 1 times n plus 2. And this will be valid for n bigger than equal to 0. So we can say that A2 will be minus A0 divided by, see if I replace n with 0 in this equation, then I'll have A2 equals minus A0 over 1 times 2. A3 similarly will be minus A1 divided by 2 times 3. A4 would be minus So this one, if I replace n with 1, then I'll get this. If I replace n with 2 in this equation, replace n with 2, then I'll get a4 equals minus a2 divided by n is 2, so 3 times 4. But a2 itself was minus a0 over 1 times 2, then divided by 3 times 4. And there's also extra minus here, so it becomes plus a0 over 1 times 2 times 3 times 4. And that is going to be 4 factorial. So a4 is a0 over 4 factorial. Now let's proceed to the next index. N equals 3. If I replace n with 3, then I'll get a5 equals minus a3 divided by 4. So n is 3, so it's going to be divided by 4 times 5. 4 times 5. a3 itself was minus a1 over 2 times 3. So minus a1 over 2 times 3 divided by 4 times 5. Minus cancels with minus. Divided by 2 times 3 times 4 times 5, that's 5 factorial. Now if I replace n with 4, a6 will be minus a4 divided by 5 times 6. But a4, I had it here as a0 over 4 factorial. So then I'll get minus a0 over 4 factorial divided by 5 times 6. That's minus a0 over 6 factorial. 4 factorial times 5 times 6 is 6 factorial. Similarly, if you replace n with 5, you'll get a7 equals minus a1 over 7 factorial. So see, I had 2 minus terms here, then 2 plus terms, again 2 minus terms, and this continues. Denominators are always same as the index here. If it's 7 here, then denominator is 7 factorial. If it's 6, then it's 6 factorial, and so on. So I think you can guess the next terms. Continuing this process. What do we get? Let's say a8 would be, so we had 2 minus, now we'll have 2 plus. a0 over 8 factorial. See, the even numbers, the even indices are in terms of a0, odd indices in terms of a1. Odd indices in terms of a1, even indices in terms of a0. So a8 equals a0 over 8 factorial, a9 equals a1 over 9 factorial, a10, now again, so this one 2 plus terms, again we will have, after this I'll have 2 minus terms, minus a0 over 10 factorial, a11 minus a1 over 11 factorial, and so on. So what will be the final answer then? So here we have y equals sigma an x minus x0, x0 is 0, so an x to power n, and from 0 to infinity. Then now let's see, a0 and a1 are my arbitrary constants. I will just leave them as a0 and a1, but I found everything else like a2, a3, a4, a5, all the remaining coefficients, I've already found them in terms of a0 and a1. So a0 and a1, I won't touch them, so just leave them as a0 and a1. So this will be a0 plus a1x. So don't touch them. But then A2 was minus A0 over 2 factorial. A3 was minus A1 over 3 factorial, and so on. So A minus A0 over 2 factorial x squared. And then A3, what was A3? A3 was minus A1 over 3 factorial. X cubed. And then A4. So what was A4? A4 was A0 over 4 factorial. So plus A0 over 4 factorial x to the power 4. A5 is A1 over 5 factorial x to the power 5. A6 is minus A0 over 6 factorial x to the power 6 minus then A7 is minus A1 over 7 factorial x to the power 7. And now I can rearrange the terms. So the terms that have A0 in common, this term, this term, this term, okay. Right with one check mark here. So this term, this term, this term, this term. So these terms I can factor A0 out. And these terms I can factor A1 out. Then what will I have? I'll have A0 times 1 minus x squared over 2 factorial. And then this one plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial plus A1 times, now the terms that have A1 in common. So as we said, this one, this one, this one, this one, and so on. So it's going to be A1 times x minus x cubed over 3 factorial, x to the power 5 over 5 factorial, minus x to the power 7 over 7 factorial. Now this one is the Taylor expansion of cos x, and this one is Taylor expansion of sine x. Taylor expansion of cos x, this one Taylor expansion of sine x. So what will be the answer then? The answer will be A0 times cos x plus A1 times sine x. Which was the answer that we were expecting before solving the equation. So we used a similar process for the previous example, wrote the function in terms of sigma a n x to the power n, substitute back, find the recursive relation for a n, and then use that recursive relation to find all a n's in terms of a0 and a1. And then the solution will be like a0 cos x plus a1 sine x in this case. Because once we wrote the solution, we detected the Taylor expansion of cos x here, and we detected Taylor expansion of sine x here, and therefore we could write the final answer or the general solution in this form. So this is the general solution of y double prime plus y equals 0. Now let's look at the next example. Next example, let's say we want to solve or find the general solution of y double prime minus xy equals 0. Y double prime minus xy equals 0. Near, find the general solution of this near x0 equals 0. So this time in the question, previous examples, x0 was not given, we had to choose it, but here x0 is given. X0 is given as 0. So the answer is, x0 is given as 0. So first we need to check whether x0 is an ordinary point for our ODE or no, because the procedure or recipe that we provided is valid as long as we have an ordinary point for our ODE. So here x0 is 0, and this is an ordinary point. So note that x0 equals 0 is an ordinary point for this ODE. Why is it an ordinary point? Because P of 0 is 1, which is non-zero. See, P of x again, in this case, is the constant function 1. The coefficient of y double prime is constant function 1. So P of everything will be 1, which is non-zero. So we can use the procedure and we can write y as sigma an x to the power n, and from 0 to infinity. So this is how we can write y, and then substitute back to find the recursive relation for an. Substitute back. So y prime will be sigma n an x to the power n minus 1, and from 1 to infinity. And then this will be same as sigma n, or first let me find y double prime as well, then I can change the indices. So y double prime will be derivative of this function, and that will be sigma n minus 1 an x to the power n minus 2, and from 2 to infinity. And if I change n to n plus 2, then I'll have sigma n plus 1, n plus 2 times n plus 1, an plus 2, x to the power n, and from 0 to infinity. Now if I substitute back, what do I get? Then I'll get sigma n plus 2, n plus 1, an plus 2, x to the power n, minus x times y prime. So x times this, so x to the power n minus 1 here will change to x to the power n. When you multiply this with x to the power n minus 1 changes to x to the power n. Sorry, minus xy, so I have to multiply this one with x, so then x to the power n will change to x to the power n plus 1. So then I'll have minus sigma an x to the power n plus 1, and from 0 to infinity. So this term is y double prime, and this is xy. Why is it xy? Because y is this. If I multiply with x to the power n changes to x to the power n plus 1, but everything else remains the same. So sigma a n x to the power n plus 1 equals 0. All right, now we can see that the powers do not match here because one power here is n, the other one is n plus 1. So these powers, we said that they have to match so that we can add the coefficients. But right now, these powers are different. So how can I adjust them so that they become same power? Well, I have two ways to do that. So one way is to change this n to n plus 1. If I do that, the starting index will shift 1 unit to the left, becomes -1. I don't want a negative starting index here. So in this topic, when dealing with power series, we don't want negative starting index. So I will not change this n to n plus 1. But instead, if I change this n plus 1 to n, or in other words, if I change n to n minus 1 here, then the starting index will shift to the right. So instead of starting with 0, I will start with 1, which is okay. So let's proceed with this solution. Change n to n minus 1 here. And then what do I get? If I change n to n minus 1, then this sigma will be sigma an, sigma n plus 2 times n plus 1, a n plus 2 x to the power n from 0 to infinity, minus sigma n from 1 to infinity, a n minus 1 x to the power n. I've changed n to n minus 1 here. So a n minus 1 x to the power n from 1 to infinity equals 0. Now these powers match, which is good news, but the starting index now, they won't match, but I can easily solve that problem because sigma n from 0 to infinity means I can replace n with 0, then plus sigma n from 1 to infinity. So we're using basically this formula that sigma bn n from 0 to infinity is same as b0 plus sigma bn n from 1 to infinity. If you want to add all the indices from 0 all the way to infinity, you can start with index 0 and then add all the indices from 1 to infinity. So if I replace n with 0 here, what do I get? So I will get 2 times 1 times a2 times x to the power 0, which is 1. So 2 times 1 times a2 plus sigma, the same sigma this time from n from 1 to infinity, and from 1 to infinity. And then the other sigma remains the same. So minus sigma n from 1 to infinity, a n minus 1 x to the power n equals 0. So we broke down this series as n equals 0, which is this term, plus the remaining term, which is n from 1 to infinity. And why did we do that? Because when we want to combine the sigmas, the powers must match. Also, the starting indices must match. So right now the powers match, but the starting indices didn't match. So that's why we separated or broke down this series as the term with n equals 0 and then the remaining terms, so that the series now starts with n from 1 to infinity, which matches exactly with this series. So now I have two series, both from 1 to infinity, and both of them, the power of x is n. And then what do we get? So now I can combine these two series, both with the same power of x and both with same starting index. So then I'll get 2a2 plus sigma n from 1 to infinity, and then n plus 2 times n plus 1, an plus 2 minus an minus 1, x to power n equals 0. So now I can compare the coefficients in the left-hand side and right-hand side. Right-hand side, I have constant function 0, which means all the coefficients in the left-hand side must be 0. So we can say that 2a2, which is the constant term in the left-hand side, must be 0. And also this coefficient here must be 0, which means n plus 2 times n plus 1, an plus 2 minus an minus 1 must be 0. And that gives me an plus 2 equals an minus 1 divided by minus n plus 2 times n plus 1. And this has to be valid for n bigger than equal to 1. Because this series starts with 1. This series here starts with 1 to infinity. So that means this coefficient has to be 0 starting from n equals 1. So we got this term equals 0 and this equals this for n bigger than equal to 1. And 2a2 equals 0, of course, means a2 equals 0. And an plus 2 is equal to this term. Now let's see whether we can find the remaining coefficients in terms of two arbitrary constants. Here we need two arbitrary constants. So let's find all ans in terms of two arbitrary constants. Let's say a0 and a1. Again, see, remember we have a second order differential equation here. So we need two arbitrary constants. I can call them a0 and a1 and then find all the remaining coefficients in terms of these two. Now if we replace n with 1 in our equation here, then I'll have a3 equals a0, n is 1, so a0 over 3 times 2. So this will be a3 in terms of a0. So, and remember our goal was to find all the coefficients in terms of a0 and a1. Now if I replace n with 2 here, then I'll get a4 equals a1 over 4 times 3. If I replace n with 2, I'll get a4 equals a1 over 4 times 3. Now what about a5? If I replace n with 3, left-hand side becomes a5, right-hand side becomes some constant times a2. But remember, a2 is 0. So a5 will be some constant times a2. Anything times 0 is 0. So a5 will be 0 as well. Now what about if I replace n with 4? Then I'll get a6 equals a3 over 5 times 6. But what was a3? a3 was a0 over 2 times 3. So then I'll get a0 over 2 times 3, 5 times 6, because a3 is a0 over 2 times 3. Similarly, if I replace n with 5, a7 I can be found in terms of a4. And a4 itself was a1 over 4 times 3. So a1 over 4 times 3, then divided by 6 times 7. So this will be a7 in terms of a1. A8, if we replace n with 6, we'll see that A8 is equal to some constant times A5. If you replace n with 6, A8 will be some constant times A5, but A5, we already know it's 0. That means A8 will be 0 as well. So if I continue this process, what can I observe? Well, A9, well, look at, for example, here, A6. Look at if the indices. If this index is 6, the last number in denominator is also 6, which matches with this index. Then it's times 5, which is 1 before 6. Then 4 is missing here in denominator, and then I'll have 3 times 2 as well. So this will be the denominator for A6. Similarly, for A7, the last number in denominator matches with this index. Then it's 1 before that 6. Then one number is missing, 5 is missing in this case. Then 4 times 3, and so on. So if I want to write what A9 is, the last number in denominator will be 9 times 1 before it, which is 8. Then one number is missing, that means 7 is missing. Then 6 times 5, then 4 is missing, then 3 times 2. And that will be the denominator for A9. And numerator is A0, see? Numerator for A3, A6, A9 are A0, and numerator of A4, A7, and all those terms are A1. So this will be A9 equals A0 over this denominator. What about A10? For A10, I need A1 in numerator because like I said, you know, for A4, A7, A10, so these terms have numerator of A1, and denominator is 10 times 9, because the last number in denominator should match with this. So if this is 10, this will be also 10 times 1 before it, which is 9, and then one number missing, 8 is missing, then 7 times 6, then 5 is missing, 4 times 3, and so on. So 10 times 9, 7 times 6, 4 times 3, then A11, again 0. Similarly for A12, 12 times 11, this number matches with this, times 1 before it, 11, then one number missing, 10 is missing, then 9 times 8, then 7 missing, 6 times 4, 5, then 3 times 2. For A13, 13 times 12, one number missing, 11 is missing, 10 times 9, and so on. And then 14, A14 again is 0. So we'll have 2 non-zero terms, then 1 0 term, and so on. So if I want to generalize this, I can say A3n is equal to A0, because what is the pattern? The pattern is the indices that are multiple of 3 have A0 in numerator, like A12, and the one before it A9, and the one before it A6. So the indices that are multiple of 3 have A0 in numerator. And what about denominator? As we said, the last number in denominator matches with this index. So the last number is 3n. The one before it is 3n minus 1, 1 before 3n. Then one number will be missing, 3n minus 2 will be missing. Then I'll have 3n minus 3. I can write a longer denominator so that this can be fit. So 3n minus 1, then 3n minus 2 will be missing. 3n minus 3, 3n minus 4. And the first two ones are 2, 3, 6 and 5, and then 2 and 3. So then 6 and 5, 3 and 2. So this is for A3n. Now for A3n plus 1, So if the index is a multiple of 3 plus 1, like 13 or 10, so these indices which are multiple of 3 plus 1, they have a 1 in numerator. So a1 over, and what will be the denominator? As we said, the last number in denominator matches the index. The one before it is 3n. And then one number is missing, 3n minus 1 will be missing, then 3n minus 2. Then 3n minus 3. And the last two numbers will be 6 and 7, 4 and 3. 7 times 6. 4 times 3 here. And then a3n plus 2 will be always 0. If the index is a multiple of 3 plus 2. Remember the first index, which was 0, was a2, which is a multiple of 3 plus 2. Then the next one, which is 0, is a5, which is again multiple of 3 plus 2. 5 is multiple of 3 plus 2. Then 8 is also multiple of 3 plus 2. All these indices, or 11, all these indices lead to 0. So a3n plus 2 will be 0. So we can find a general solution then. So thus, the general solution can be written as follows. So we know y is equal to sigma an x to power n, and from 0 to infinity. So then I'll have a0, a0, let's leave it as a0, a1, let's leave it as a1. And then a2 is 0, but the next term is a3. a3 was a0 over 3 times 2. So plus a0 over 3 times 2, x to power 3. And then we have a 4, which is a 1 over 4 times 3. a4 was a1 over 4 times 3. So a1 over 4 times 3, x to power 4. And then a5 is 0. Then I'll have a6. a6 was here, a0 over 2 times 3, 5 times 6. 2 times 3, 5 times 6, x to power 6. And then a7 will be a1 over, for 7, I had a 1 over 3 times 4, 6 times 7. X to power 7. And then the next one will be 0, a8 is 0, so plus dot 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 plus, and then I can say a3n over 3n. Now for 3n, or a3n was basically a 0 over 3n here, 3n minus 1, 3n minus 1, all the way to 6532. 3n 6532 x to power 3n. Because this coefficient here is a3n, but I just saw what a3n is. a3n is a0 over this denominator. So I replace it here, a0 over that denominator, which is a3n times x to power 3n. And then I have a3n plus 1. a3n plus 1 is a1 over this denominator, so plus a1 over 3n plus 1, 3n, all the way to 7643. X to power 3n plus 1, and so on. So now I can match the terms that contain a0, factor a0 out, and the terms that contain a1, factor a1 out. And then I'll be left with what? So a0 here, a0 here, a0 here, a0 here, and similarly for a1, a1 here, a1 here, a1 here, a1 here, and so on. So then I'll have a0 times 1 plus x cubed over 3 times 2 plus x to power 6 over 3 times 2, 6 times 5, and then x to power 3n over 2 times 3, 5 times 6, 3n minus 1, enough space here, so it's this. So this is a0 times this plus a1 times. Now what about a1? It's going to be x plus x to power 4 over 3 times 4 plus x to power 7, 3, 4, 6, 7. And then x to power 3n plus 1 divided by 3, 4, 6, 7. All the way to 3n, 3n plus 1. So I can write this one as, let's say, a0, let's say y1 of x plus a1 y2 of x, where y1 of x is equal to 1 plus x cubed over 3 times 2 plus x to power 6 over 3 times 2, 6 times 5. And y2 of x is x plus x to power 4 over 3 times 4, x to power 7 over 3 times 4, 6 times 7. And then x to power 3n plus 1. 3, 4, 6, 7, 3n, 3n plus 1. And here the last term was, not the last term, but the generic term was x to power 3n, 3, 2, 6, 5, 3n minus 1, 3n. Both of them plus dot, dot, dot. So both of them are series, meaning that there is no last term. But I can write a generic term in terms of like x to power 3n over this, so that if I replace n with 1 here, I'll get this term. If I replace n with 2 here, I'll get this term, and so on. but there's no last term. So after you write the generic term, remember to write plus dot dot dot. Again here, generic term, then plus dot dot dot. So this one, this function, I called it y1 of x. This function, I called it y2 of x. So then general solution can be written as a0 y1 of x, a1 y2 of x. So this is the general solution. General solution of y double prime minus xy equals 0. And y1 of x and y2 of x are these functions. So previous example, we could write y1 of x as, let's say, sine x, and or y1 of x as cos x, y2 of x as sine x, for example. For the example before that, we could write the series as e to the x. But this one, you know, the series, we have to leave it as a series because we cannot write it in terms of the elementary function. We cannot write it in terms of sine x, cos x, e to the x, or it's not a polynomial either. So we have to leave it as it is. So in this, so here, leave your series like y1 of x and y2 of x as series. And as we are not able to write these functions in terms of the elementary functions. Such as sine x, cos x, e to the x. So we'll leave them as they are. All right, let's look at the next example. Find the general solution of this equation, this ODE, y double prime minus 2xy prime plus 2l times y equals 0. So here L is a positive integer. Using power series method. So again, this question, x naught is not given. We have to choose x naught. Again, if we can choose x naught to be 0, then go ahead and choose it as 0. Here, p of x is 1. P of x equals 1. Coefficient of y double prime is 1. So that means p of 0 is also 1, which is non-zero. So that means we can choose x naught to be 0 because an ordinary point. Ordinary point of this ODE. Then we can write y as sigma an x to power n, and from 0 to infinity. In general, y is sigma an x times x minus x0 to power n. But here x0 is 0, so we can write it as sigma an x to power n. Then what will be y prime? So y prime will be sigma n an x to power n minus 1, and from 1 to infinity. And y double prime will be derivative of this function, which is sigma n minus 1 an x to power n minus 2, and from 2 to infinity. And the equation is y double prime minus 2xy prime plus 2ly equals 0. We can substitute back. So what do we get? Y double prime minus 2xy prime plus 2ly equals 0. And then I'll have a sigma n minus 1 a n x to the power n minus 2. And from 2 to infinity minus 2xy prime. So if I multiply this with x, then I'll get minus 2 times sigma n a n x to the power n from 1 to infinity. I multiply this with x, so I got n a n x to the power n. And then, so y double prime minus 2x y prime plus 2ly. So this is y. I just need to multiply it with 2l. So plus sigma 2l a n x to the power n, and from 0 to infinity equals 0. But now I have to rearrange the terms and combine the terms, but in order to combine them, I need the powers and the starting indices to be same. But right now, they are not the same. For example, this one is n minus 2, but these two are n. And the starting point, this one is 2, this one is 1, this one is 0. So how can I figure this out? So let's think about each sum and think about it, how it starts. Does it start with a constant term or does it start with x term? So if, for example, all of them start with x term, then I can match them together because I just will need a shift. And I just need to rewrite the sigma. But for example, if one of them start with constant term and one of them start with x term, then I cannot match them because the problem is not just rewriting the sigma. If it's a constant term and the x term, they cannot be matched. So let's see each sigma starts with which term. So look at the first sigma. Start with 2, but it's n minus 2 here. So I start with x to the power 0, which is a constant term. And then I'll have x term, x squared term, and so on. So this sigma here can be written as constant term plus something times x and so on. What about this one? This one is x to the power n, start with 1. So I start with x term. Because if n is 1 here, I'll have x, then x squared, and so on. So this one starts with something times x plus something times x squared plus. And what about this one? Starts with 0, n equals 0, and it's x to the power n. So x to the power 0 is constant term. So it starts with constant term plus something times x plus something times x squared, and so on. So two of them start with constant term and one of them start with x term. So if I break down this sigma and this sigma as a constant term plus the x terms, plus the terms that start with x, and this one start with x, then I can match them. But constant term have to be separated because only these two sigmas include constant term, not this one. So let me break down this sigma and this sigma as constant term plus some x term. And then I can separate the constant terms together. And then I can combine the remaining terms and write it as one sigma. So I can say now, break down the first and third sigma above as constant term plus remaining terms. Then combine matching terms. So first sigma, the constant term, if n is 2, then I'll have 2a2 x to the power 0, which means 2a2 plus, then, so I have separated n equals 2. Then what will be left? N from 3 to infinity, because 2 is already separated. So n equals 3 to infinity, n minus 1, a n x to the power n minus 2 plus or minus, so this one, I can just write it as it is because I didn't have to break down this sigma. I just had to break down first and third one. So minus 2 sigma n a n x to the power n from 1 to infinity. And then for this sigma, I can break it down again, constant term. N is 0, I'll have 2la0. So plus 2la0. And then n from 1 to infinity of this sigma. So plus 2lan x to the power n from 1 to infinity equals 0. So now these two terms can be combined together. And then the remaining can be combined. I just need to, before combining, because this one and this one, obviously they match, they have the same power and same starting index. But this one will have the same power, same starting index, after I just simply change n to n plus 2. Because if I change n to n plus 2, this becomes x to the power n, matching with this. And we know that if I change n to n plus 2, the starting point will shift 2 units to the left. And therefore, this will be also starting from 1 to infinity. So I can write this one as, so let me combine these two together. So 2a2 plus 2l a0. And then for this sigma, I am changing n to n plus 2. So it becomes n plus 2 times n plus 1. A n plus 2 x to the power n from 1 to infinity. And then sigma or minus 2 times n a n x to the power n from 1 to infinity. And then this sigma plus 2l sigma 2l a n x to the power n from 1 to infinity equals 0. So now all these three sigmas have same starting index and same power for x to the power n. So they can be combined together. So I can say 2a2 plus 2la0 plus sigma n from 1 to infinity. And then just add these coefficients, n plus 2 times n plus 1, a n plus 2 minus 2n a n plus 2l a n x to the power n equals 0. Minus 2n a n plus 2l a n x to the power n equals 0. So that means, well, right-hand side is identically 0 for every x. So that means left-hand side, all the coefficients must be 0, which means constant term must be 0. And also every coefficient must be 0. So n plus 2 times n plus 1, a n plus 2 minus 2n a n plus 2LAN equals 0. This should be valid for n bigger than equal to 1, because the sigma here starts with 1. So this formula has to be valid for n bigger than equal to 1. And then I'll have an plus 2. So if I take an to the other side, an plus 2 will be equal to 2NAN minus 2LAN divided by n plus 2 times n plus 1. And this can be written as 2n minus 2l times an divided by n plus 2 times n plus 1. So this has to be valid for, again, n bigger than equal to 1. And we got 2a2 plus 2la0 equals 0, which means a2 will be minus la0. This is one equation, and for n bigger than equal to 1, we have this recursive relation. So to be continued next time. So we already found the recursive relation for an. Now we are ready to find all the coefficients in terms of a0 and a1. We have done this in previous examples. Maybe for next time, try to think about it, do the calculation, see whether you can figure out about all the coefficients. This is again a second order ODE. We're allowed to have two arbitrary constants like a0 and a1, and try to see whether we can find all the remaining coefficients in terms of these two, and then find the general solution. All right, guys, so we'll continue the solution here and complete the calculation next time for this example, and we will use these recursive relations that we derived here to complete the solution. Okay, guys, so that's all for today. Thank you, and see you next time.